Hey there, students. Welcome to Psych 53 Lab, Module 5, where we'll be discussing analysis involving categorical dependent variables. And really, just short, we're going to be learning how to do logistic regression. So my objectives today are to do a quick review of logistic regression, then we'll talk about odds ratios, and then we'll go into our classic coding tutorial. So, logistic regression is used when you have a binomial outcome variable. Until now, we've always assumed that our outcome variable is continuous. Here now, it either takes on a 0 or a 1, and it's very specific that it needs to take on a 0 or a 1 in logistic regression. And pretty much what's going on is it uses a logit link to link the categorical outcome with the predictor variables. And from this, you can derive these interpretable odds ratios from logistic regression. And that's really where my focus is going to be on today, is getting those interpretable odds ratios. It's super neat. It makes logistic regression really fun, and it's easy to attain these odds ratios when you're doing it. But as you can see, linear regression really doesn't do a very good job because it's not constrained to these 0 and 1 bounds, and you're not just mapping on a probability. Whereas logistic regression constrains your analysis to the 0 and 1 bounds, and you're able to get probabilities from this. And really the big focus of today is how we're going to be obtaining these odds ratios and how we interpret these odds ratios. So odds ratios range from 0 to infinity. And as you can see from this chart here, what they do is they map onto probabilities. The lower the odds, the less the probability of it happening. The higher the odds, the more higher probability of it happening, where it never actually reaches that 1 probability of 1, which means 100% probability, but it gets very close the higher and higher you go, and it'll keep hugging that line as far as it can go. So this really goes from 0 to infinity, this line. So the way that you interpret these odds ratios is that an odds ratio lower than 1 indicates that an event is less likely to occur. So when you're saying an odds ratio as less than 1, you're saying that that event is less likely to occur. So whatever is coded as 1 in your outcome variable is less likely to occur. Now what you can do is you can take the inverse of that and saying the odds of it not occurring as well. And I'll show you how to do that later. And when I say take the inverse of something, I mean taking 1 over whatever the odds ratio is. So that turns it into a number above 1. You say the event of it not occurring. An odds ratio above 1 indicates that an event is more likely to occur. So saying that the probability of it occurring, if you have an odds ratio of 2 times, it says 2 times as likely of occurring as another event or something like that. An odds ratio of exactly 1 indicates that there's no relationship between the predictor and the outcome variable. Essentially, the odds of it happening are exactly the same or if it's not happening. So in logistic regression, we're going to be doing something called exponentiating our coefficients to obtain these odds ratios. So what's going to happen is we're going to get this table of coefficients that aren't really readable, but we're going to do something called exponentiating them in order to obtain odds ratios so that are interpretable that map onto these probabilities. So let's go ahead and get started with R. So we'll go and open up our studio and create a new project. Make sure to save that correct subdirectory. Module 05, create project. Then we'll go ahead and download the data set, which should be on your canvas. Drill down to module 5. In the module 5 lab, logistic2.csv is the name of the data set we'll be working with today. Okay, and then we'll go to desktop, Psych 53, module 05, save. There we go. Go ahead and exit out, and we can confirm that it's saved in there. Yep, we see logistic2.csv in there. Go ahead and create a new R notebook. Go ahead and delete this unnecessary text. We can go ahead and name this notebook. We'll name it Logistic Regression. We'll go ahead and get the table of contents, POC : yes. Let's go ahead and save this. Name it Module 5 Notebook. Okay. And I'm going to go ahead and I'm just going to open up some notes. So just bear with me for a little second here while I get some notes up. Okay, there we go. All right, let's go and see what's next on our PowerPoint. So today we're going to be using two libraries. It's the tidyverse and psych package, so nothing new. So hashtag load libraries. Insert a new R chunk. So we're going to be using library, psych, library, tidyverse. Go ahead and play that. Okay, I'm going to go and play that again just to get rid of the output. And then we're going to go ahead and read in our data set, which is the logistic2.csv. And just so you know, this is a simulated data set where n is equal to 164, and we have 5 total variables. Y is a binary variable coded as 0 or 1. X1 is a binary variable coded as 0 or 1. And X2 through X4 are all continuous variables as well. So we're going to get some practice on reading it when there's a binary variable as your predictor and when there's a continuous variable as your predictor. But let's go ahead and read in that data set first. So do hashtag import data, insert a new R chunk. We're going to name it LR, use our assignment operator, do read underscore CSV, use parentheses, and then it's going to be capital L, logistic2.csv. I'm going to read that in. There we go. And as we said, we have 164 observations of 5 variables. This is a simulated data set. Okay, let's see what we got next. Yeah, and I just wanted to get a good look at our data set. So as you can see, in our Y outcome, notice how it's a series of zeros and ones. It's very important that your outcome variable is coded as 0 ones. If it is coded as 1 and 2, you're going to have to go ahead and mutate it so that 1 means the event occurs, 0 means the event didn't occur. So here we're just saying 1 is the event occurring, 0 is the event not occurring. And then we have X1, which is just a binary variable as well, X2, which is continuous, X3, which is continuous, and X4, which is continuous. Okay, so it's very essential that your data be set up in this way if you're going to be running logistic regression. And I also wanted to introduce you to the GLM function today. So before we've always been working with the LM function, which is just for linear modeling. Now this stands for general linear modeling. And what it looks like is it looks very similar to your LM function. The only difference is that we're indicating something called a family now. Now you need to indicate that your family is binomial, which essentially means that it has 0 or 1 for your outcome variable. Is essentially what it means. And then there's other families that you can indicate as to. There's neg-bin for negative binomial. There's Poisson regression, but we're going to be working specifically with binomial regression, which stands for logistic regression. So that's really the main difference between the thing. You're going to see that this looks very similar to how we did linear regression in the past, but we're going to be using the generalized linear model now, and with the family equals binomial. Okay, so what we're going to do is first, actually I don't have it in these slides, but first we're going to go ahead and just describe the data set. Describe data. So do insert new R chunk and do describe LR. There we go. So as we can see, the proportion is 69.69. So if you take the mean of a 0 and 1 variable, it just gives you the proportion. So 69% of the variables are coded as 1. 46% of the variables are coded as 1 for X1, and then we have a mean value of 6.15, mean value of 1.42, and a mean value of 3.17. And as you can see, your binary variable takes on only zeros and ones. Okay, so the first thing we're going to do is we're going to start simple. We're going to run a logistic regression model and talk about the interpretations of it. Okay, so hashtag, let's do practice logistic regression. We'll do hashtag model1 just a binary variable as a predictor. Insert new R chunk. So what we're going to name this is we're going to name it, let me just see what I named it here. We're going to call it log underscore mod1. Use an assignment operator. We're going to use the GLM function. And it looks very similar to how we regressed our variables with the LM function. We do Y regressed on X1, comma, family equals binomial, comma, data equals LR. So we run that, that'll give us a new list. So we ran that correctly, so it gives us a list 30, and this is a generalized linear model right here. Then, just like we did with the LM function, we use the summary function, log underscore mod 1. We can use the summary function or output the results. Okay, so let's look at this now. So we can see it up on the slideshow now. This should have the exact same results. So what we can see from this is that it's displaying something called the log odds of the predictor variable on the outcome of y. And what it means by the log odds is that these aren't really interpretable quite yet. So there's no sense in looking at the estimates and whether or not they're interpretable or not. But what is important is to look at our p-value here and say, yeah, okay, well, we have a significant value of x1, but now we got to say, well, what can we do to this so that they can be interpretable? What we're going to do is do something called exponentiating them. And we exponentiate these log odds in order to get interpretable odds ratios. So what we're going to do is we're going to dig into our log mod list and actually grab the coefficients and exponentiate them. So that's what is exactly what's going on here. So coefficients log mod means that it's going to go grab from the log mod 1 object the coefficients, and this exp, since we're going to exponentiate those coefficients. So just a little heads up as to what's going on. So you get this log mod 1, and you see this coefficients, and there's the values that are over here. We're going to take these coefficients and we're going to exponentiate them. That's all that this is doing. So what we do hashtag, we'll do 3 hashtags, hashtag, exponentiate the coefficients and confidence intervals. So go ahead and insert a new R chunk. So what we do is we do exp, we do coefficients, and then log underscore mod 1. I'll do this first, and then we're also going to exponentiate and get the confidence intervals as well. So I go ahead and exponentiate that. So we get an intercept of 1, which says that pretty much, and as we can see, I have it here, when all the x variables are 0, the log odds are 1 times as likely of developing the outcome of y, meaning that the odds are completely even of developing the outcome of y. So this is not statistically significant. And one of the ways that you can tell if it's statistically significant or not is in our confidence intervals, which we're going to calculate in a second. But essentially, confidence intervals, if they contain the value of 1, that means that it's not significant. Or you can actually just look at your model as well and tell you whether or not it was significant or not. So this is super not significant as well. And then our x1 is saying those coded as 1 are 9.86 times as likely to develop the outcome as y as compared to those coded as 0. This is statistically significant, but I want you to notice with this confidence interval, when we calculate it, it's a very wide confidence interval. So let's go ahead and calculate that confidence interval. So we're going to do exponentiate conf int log underscore mod 1. And let's just run this whole thing. And it's always going to have that waiting for profile to be done. I don't know why it's there, but it's just something that's always there. Don't worry about it. It's just always going to be there. But we have our confidence intervals associated with this as well. So we get the confidence interval for the intercept, which says that these values can range anywhere from 0.657 to 1.52. And same with our x1, saying these values can range from anywhere from an odds ratio of 4.30 to 25.789. So that's a pretty wide confidence interval, which gives us kind of some like, ooh, maybe this isn't the best thing to be modeling, honestly, when we see that. But the important thing is that we got our coefficients and we have interpretable odds now. So remember, this 9.857, that means that those that are coded as 1 in this predictor variable are 9.86 times as likely to develop the outcome of y as compared to those that are coded as 0. So it's saying yes, if they have the yes to this, they're 9.86 times likely to develop the outcome of y compared to those coded as 0. Notice how I make that comparison of coded to 0. That's a pretty essential part to it. So what we're going to do next is we're going to add in a continuous predictor as well. So let's go ahead and do this again. So do hashtag. Let's see, we'll do model 2, 1 binary predictor, and 1 continuous predictor. We'll do insert an R chunk. So we're going to regress. Let me just see here. x1 and x2. So we're going to name this log underscore mod 2, use an assignment operator, use the GLM function, and we do y regressed on x1 plus x2, comma, family equals binomial. Again, that's just setting it so that we're doing logistic regression. Data equals LR. And then we take the summary of that. It's spell log mod 2. All right, and we play that. Okay, so again, we get these coefficients here that they're called the log odds, essentially, that we'll be taking this from. There's log odds. So what we're saying here, and I have the interpretations here. So yes, as I said, there's a log odds, and we see that x1 is statistically significant. However, x2 is not statistically significant. But we'll have a better understanding of these when we get the OR odds ratios and confidence intervals. So what we'll be doing is, again, we're going to be exponentiating our coefficients and then getting and exponentiating the confidence intervals as well. So we'll do hashtag, hashtag, hashtag. Let me see what I wrote up here. We'll just go ahead and copy this. Exponentiate the coefficients and confidence intervals and insert a new R chunk. Okay, so the way that we do that, we do exp. We're doing nested functions here, coefficients, and then log underscore mod 2. And then we'll do exponentiate conf int. That's going to be log underscore mod 2. So we run that, and we get our odds ratios, which are up top here, and our 95% confidence intervals, which are down here. So it's a lot easier if I just interpret them from the actual PowerPoint slide. So our intercept is saying when all the x variables are 0, the odds are 1.56 times as likely of developing the outcome of y. This is not statistically significant. There's two ways we can tell that. Either A, by looking at the significance here for the intercept, or looking at the confidence intervals and seeing if they do contain 1. So 0.415 to 6.15 contains the confidence interval, contains a value of 1, saying that it's possible that the odds ratio could be 1, meaning that there's an equal chance. So it's not statistically significant. The next thing we're going to look at is our x1 variable. So it's saying after controlling for all variables in the model, so pretty much after controlling for x2, those coded as 1 are 9.74 times as likely to develop the outcome of y as those compared to those coded as 0. And this is statistically significant. Again, so this is where I got that value from right here. Again, we can look at either the coefficients for x1. We're not interpreting the log odds here. And what we'll see is that, okay, yes, it is statistically significant, or we can look at the confidence intervals and see that they do not contain a value of 1. They go from 4.24 to 25. So this, again, is pretty large confidence intervals, saying that it can either be 4 times as likely of developing the outcome or 25 times as likely of developing the outcome. And that's pretty big. That's a pretty big difference to do. So you have a little bit of like wariness when you're looking at these confidence intervals. And then our last one, x2, which is a continuous one, and I'll give you the interpretation of that, saying after controlling for all variables in the model, so controlling for x1, for every 1 unit increase in x2, there's an expected increase of 0.931 times of developing y. Or, because I said it's below 1, we can also take the inverse of that, which just says 1 divided by 0.93, saying, or we can take the inverse of that and say that for every 1 unit increase in x2, there's a 1.07 increase in the odds of not developing the outcome of y. That's what that inverse does to you. I like to always take the inverse whenever they're below 1. I think it's a little bit more easy to interpret. 1.07 times increase in not developing the outcome instead of saying a 0.93 increase in developing the outcome, which is really a less of an outcome. So that's what I like to do. But anyways, this is not statistically significant. As you can see, the confidence intervals contain the value of 1. Okay. Let's do one more model, okay? We're going to add in 2 extra variables here. We're going to name this log mod 3. So we'll say hashtag model 3, hashtag model 3, one continuous, or let's say one binary variable and binary predictor. and 3 continuous predictors. So again, we'll do that model. So we're going to name this log underscore mod 3. And then we're going to do GLM y for guessed on x1 plus x2 plus x3 plus x4, comma, family equals binomial, comma, data equals LR. And then we can go ahead and get a summary of our log mod 3. Log mod 3. So we go ahead and run that. And there we go. So we see that there's only two significant coefficients, x1 and x4. Our intercept isn't significant, and neither is x2 or x3. So we can go ahead and look at that. And again, these are log odds, so they're not really interpretable yet. But again, we're just going to go ahead and exponentiate our models. So we'll do copy and paste this again. Paste that. Okay, so we do exponentiate, exp, coefficients, and then log mod 3, and do exponentiate, const log underscore mod 3, and we'll get our interpretable odds ratios again. Okay, so I'm going to go ahead and go back to the PowerPoint slides, but it should look exactly the same. But what we're saying is, so for the intercept, when all the x variables are 0, the odds are 0.421 times the likelihood of developing the outcome of y. Or again, we can take the inverse of that and state that they're 2.3 times likely not to develop the outcome of y. And this is not statistically significant. Our x1 variable is saying after controlling for all variables in the model, those coded as 1 are 5.88 times likely of developing the outcome of y, as compared to those coded as 0. And this is statistically significant because we can look at our confidence intervals and see, okay, yeah, that doesn't contain an odds ratio of 1 within our confidence intervals. X2 is saying after controlling for all the variables in the model, for every 1 unit increase in x2, there's an expected increase of 0.918 times the developing outcome of y. Or we can take the inverse of that and say that for every 1 unit increase in x2, there's a 1.09 increase in the odds of not developing the outcome of y. And then we can say the same, we can talk about x3, which is a very similar interpretation, and x4, which is also a very similar interpretation as well. And we get the confidence intervals, and we see that, okay, x3 is not significant because it contains 1 within the confidence intervals, and x4 is significant because it does not contain 1 within the confidence intervals. It goes from 1.22 to 2.76. And the last thing we're going to do is compare our models. So essentially the way that this works is it's comparing this thing called deviancy, which I think you learned about a lot in Kevin's, but deviancy is a proportion of model fit. For every time we add in a variable to the model, the deviancy decreases as well. And what we're going to be doing is using this ANOVA function within our logistic regression model and testing, does adding a variable one at a time add anything to statistically explain any of the variance, or essentially we're saying is the residual deviancy go down enough? So let's go ahead. We're going to do we'll do one hashtag, use ANOVA to compare the model deviancy. So we're going to go ahead and do insert in our chunk. We're going to do ANOVA. And unlike a logistic regression where we had to do, unlike linear regression when we had to do the hierarchical modeling, with logistic regression, what's really nice is that you can just do your full model and it'll do the comparisons for you. And then, let's see what it is. Test equals chi-square. Test equals quote chi-square. I need to make sure I got that right. Yep. Okay. Go ahead and run that. So what this is saying is that it's comparing the deviancy as an estimate of model fit between each model and the no model. So the values represent, so x1 is the model with just x1 in it. It's saying it's comparing it to a model with nothing in it. So it's saying that the deviancy of a model with nothing in it is 203.32. And then what we're saying is by adding in the x1 variable, our deviancy drops to 168.72, and this is statistically significant. For the x2, it's saying when we add in the x2 variable, the deviancy drops to 168.23, which isn't very much, and it's saying this is not a statistically different change within the model. X3 says once we add an X3 to the model, is there a statistically different change? And it's saying no, there's not a statistically significant different change. It's kind of close, it's 0.05, but it's not statistically significant. Then for X4, it says that we add in and then the deviancy drops down to 155.59, and that this is a significantly decrease in the deviancy. So really, we should be concentrating on X1 and X4 as kind of the best predictors within our model. So this comparison tells whether adding information to the null model leads to a better prediction. In this case, X2 and X3 do not significantly improve model fit. And the last thing that we can do is we can go ahead and calculate McFadden's R squared. So the way that you do that is you simply do 1 minus the deviance model divided by the deviance null. So the way that we do that, we can go ahead and go to our R and do that. I'm actually going to have R open on the same thing so I can just have all of the numbers available to me. But we'll do hashtag calculate McFadden's R squared, which is just a way of doing the proportion of variance explained. So we can go and create a new R chunk, and where these numbers come from, I'll show you right now. 168.72 divided by 203.32. So the deviance null, it's the 1 minus the deviancy of the model divided by the deviance null. So we can go ahead and get our model again. Well, actually, I think I can do this without doing this. So what it's going to be is going to be, so for model 1, McFadden 1, for our model 1, we're going to save it into an object. It's going to be 1 minus, let me make sure I get this right. Okay. Sorry. It's going to be 1 minus 168.72 divided by 203.32. That's going to be our first McFadden 1. We can really just copy this. Name this McFadden 2. And this one is going to be 168.23. So as you can see, I grabbed that 168.72 here, and the 203.32 is going to be the same across all of them. McFadden 3, 1 minus 164.54 divided by 203.32, and then McFadden 4 and 1 minus 155.59 divided by 203.32, and then we can simply output all of our things too. So I'll just go ahead and copy all this because we're going to display our objects out. There we go. And we can go run all this. We're going to have 4 new values here, and we can go and output a McFadden 1 first. So in the first model, model 1, where it's just x1 explaining the outcome of y, we're explaining 17% of the variance. In model 2, we're explaining again 70% of the variance. Model 3 comes up to 19% of the variance being explained. And model 4 explains 23.47% of the variance. And we can go and run all that. And there we go. Those are our values. So we calculated the McFadden's R squared, which is something you learned about in Kevin's lecture, but essentially it's a pseudo R squared and saying that we're explaining a certain percent of the variance in our outcome of y is really all it is. And that is it. That's everything to logistic regression that you need to know in R. So if we go to the module, go to module 5, lab, I have an assignment for you. And go ahead and start working on that and let me know if you have any questions, and if not, and thank you so much for listening. Bye-bye.